In this video, we're going to be discussing chemistry of acid and bases. This is done by Nate Martins and Cade Brower. So what this video is going to be detailing about is the differences in pH between acid and bases, how you can identify acid and bases using the pH scale. We'll be looking at a couple neutralization reactions as well. And lastly, we're going to be discussing how you can look at acid and bases and how we know it and take it further through the Bronsted-Lowry theory. So the first thing to discuss is the pH scale. Acids and bases can be determined by their pH level. The pH is a measurement of how acidic or basic a substance is. When the pH level is determined, you can look towards the pH scale to figure out if it's acidic or basic or even neutral. So the pH scale goes from 0 to 14. Acidic is 0 to 6, 0 being the highest and 6 being the lowest in acidity. Next would be 7, which is neutral. An example of this could be pure water. Basics is from 8 to 14, 14 being the highest, and then 8 being the lowest for basic. A couple of examples of substance, just to reinforce the knowledge, would be stomach acid, which would be a pH level of 2, acid rain being 4, washing liquids is 9, and finally bleach is 12. So the pH scale is color-coded, showing that the more acidic something is, the closer to red it is, and something being more basic is how purple. To visually see this, we can use an indicator. An indicator is a substance that is used that when you pour it into another substance, it will change the color, which will show the color on the pH scale. So let's say I had bleach in a beaker, and then I poured an indicator, it would show that it's 12 being purple, specifically that shade of purple. The most commonly indicator used is the universal indicator. This works in all substances, and this is the indicator that shows the color to the corresponding pH value.
Another way to determine whether a substance is acidic or basic is by using litmus paper. When litmus paper is dipped in a substance, it will change color according to whether the substance is an acid or base. Blue litmus paper changes to red when dipped in acidic substances, and red litmus paper changes to blue when dipped in basic substances. The beaker on the right contains citric acid, which caused the blue litmus paper to change to red, and the beaker on the left contains a basic substance, which will cause the red paper to change to blue. When acids and bases react, the resulting reaction is called a neutralization reaction. This type of reaction occurs when an acid and base react to form water and a salt. However, the term salt does not only refer to the table salt that we typically use. In this case, salt refers to any ionic compound that is formed from a reaction between acids and bases. Neutralization reactions are one kind of reaction that can take place even if one of the reactants is not in its aqueous form. For example, liquid HCl can react with solid FeOH3 to form water and FeCl3. The following experiment is a demonstration of a neutralization reaction.
Lastly, I'm going to be discussing the Bronsted-Lowry theory. So when we were thinking of acids and bases, we would be able to determine it by looking if the acid would contain hydrogen or the base would contain hydroxide. So now I'm going to take this further where hydrogen or hydroxide ions don't even have to be present for it to be basic or acidic. So acids go beyond just hydrogens, ions, and hydroxide ions, like I said. The Bronsted-Lowry theory was created in 1923 by Johannes Nicholas Bronsted and also Thomas Martin Lowry. This is where you get the name Bronsted-Lowry. The Bronsted-Lowry theory states that an acid and base can be determined through the compound's ability to either accept or donate protons. An acid is known to be a proton donor and a base is a proton acceptor. This theory goes even more beyond and proves that substances don't even require H or OH to be classified. As I said before, acids and bases can only be themselves when in the presence of one another. Aqueous base has the ability to gain a proton and be known as a conjugate base, and same goes for acids. So first example of on the right would be hydrochloric acid and ammonia. As you can see, ammonia, it's a base, however, it does not contain hydroxide. Hydrochloric acid does contain hydrogen, so that shows that it's acid. However, when the reaction occurs, the hydrogen from the hydrochloric acid is then transferred to ammonia, leaving just chloride and ammonium. So as you can see, the hydrogen donated itself to the base. As base is the acceptor, it accepted the hydrogen, causing it to be NH4. So this is an example of not having hydrogen and hydroxide present in a reaction. It shows how the hydrochloric acid donated a proton and the base accepted it, leading to a conjugate base and conjugate acid.